Yeah, so hi there. My name is Aarnav Sawant. I'm a high school senior at Bellarmine College Preparatory in San Jose, California, in the US. So today I'd like to present my summer research, ZQBA, a zero query boosted ambush adversarial attack on image retrieval. I want to thank AIAD for giving me the opportunity to present this research in front of so many talented people. So before beginning, this is an agenda for what I'll be covering. So we'll first start off by diving into a background of content-based image retrieval, specifically how it works. We'll then give a little bit of context into what adversarial attacks are. Uh, then we'll formulate the problem of adversarial attacks specifically for content-based image retrieval. After that, we'll explain the methodology and the techniques and challenges of crafting a successful attack for content-based image retrieval before expanding on the extensive experimentation we conducted. We'll then analyze the key insights and results and the metrics that we took away before leaving off some takeaways and further research. So here we go. So content-based image retrieval, it's a computer vision problem where given an input query image, a set of the most relevant and similar images is returned from a database of images. So just to like make really clear, you give a content-based image retrieval model one image and you get back a set of 10 images back. So when thinking about ways to approach a content-based image retrieval problem, there's three main ways. The first one is the most naive way, which would be to directly compare pixel values and compare similar images. So while this might be the simplest way, as anyone who's like attempted to do any kind of like image distance can speak about, image distance is like not a very great metric of telling similarity, especially in the pixel space. So that way is the most simple, but it's the least effective. The second way is using a convolutional neural network to classify an input image and return images in the same class. So this way can be really effective, but the problem of using a convolutional neural network is you obviously need to be able to train and you need to train and extend an image classifier on an extensive data set and with on multiple classes as well, which may not be available for certain use cases of image retrieval. And the next way is the way we'll focus on in this paper, which is specifically using a pre-trained convolutional neural network to simply extract the high-level features of an image and then to return the closest images in feature space. This would be essentially using a pre-trained CNN on a larger data set like ImageNet, extracting the feature vector, and then using some sort of distance metric like cosine similarity, Euclidean distance, or vector dot product to be able to return the closest images in this embedding space. So as we move on, we first want to go over a couple applications of content-based image retrieval. The first one is facial recognition. So consider a situation in a facial recognition system where you have a database of face images, and then when a new person scans their face, rather than having to train a classifier for each new person, what a facial recognition system will do is it will use a feature extractor to convert your image of a face into a feature vector, compare that feature vector with the feature vectors of all the other images in the database, and will then return the closest image to compare to. That will be the closest image. The second thing is inappropriate content detection. In this application, essentially, a feature extractor will convert. You'll have a set of pre-trained a set of images originally of inappropriate content. As you get a new image, you'll compare the feature vector of the new image with the feature vectors of your already like of the original images. And if it's close enough, you can assume it's inappropriate content detection. And the last example is the example we're going to talk about in this paper, which is intellectual property management, specifically in like graphic design and other forms of art, to make sure that there's no copyright infringement. What digital rights management softwares will do is they'll take an input image or like an input art from like a graphic designer or artist. They'll pass it through a convolutional neural network feature extractor to get your feature vector, and then compare this vector with all the other images in the data set to be able to determine if there is similar images and that the image has not been plagiarized. So this is a little bit of a diagram just to talk about specifically CNN-based CBIR systems. So like I mentioned earlier, so basically you have an input image, you pass it through a CNN-based retrieval model, which will give you an output feature vector. And then based on the feature vector in the feature space, you will return a set of similar images back according to some distance metric. So talking about the digital rights management system application. So say we have an attacker who is attempting to plagiarize an artwork. So what he'll do is he'll submit the artwork to a CBIR system. The CBIR system will return a set of similar images back. Then a human, a professional monitor, will go and check to see if this input image is really similar to any of the 10 images that have been returned back. And in this case, this image is pretty much the same as all the 10 images that have been returned back. So thus, he can then mark this image as plagiarism, and the hacker was not able to publish his artwork. So this brings us to our next topic, which is adversarial attacks. So specifically, if the attacker wants to get away with this form of plagiarism, he can employ this technique called adversarial attacks. So adversarial attacks were discovered by Ian Goodfellow in 2013. Specifically, what he discovered was that deep neural networks are vulnerable to immediate imperceptible perturbations to input images. So basically, you see this example here of the panda, where you have the original image of a panda. He discovered that by basically adding this noise to the panda, you get a similar panda image that is imperceptible. It looks exactly the same, but when you pass it through a CNN classifier, it classifies it as a gibbon. And then just to get into a little bit of the math for what he's doing in this case. So for training a neural network classifier, obviously the goal would be to like minimize the cross entropy loss across all parameters. So essentially in this case, what he's doing is he's back propagating the cross entropy loss function all the way back to the input image. And then by adding the signum of the gradient of the loss function with respect to the image, he can move the image in the direction that maximizes the cross entropy loss function rather than minimizing it. And that's how he accomplishes his goal of fooling the classifier. So back to our digital rights example, this is exactly kind of what the goal is of this project, is basically for an attacker to be able to add this input perturbation to the input image. And then when he passes this image with this noise added to the image, we'll get a set of 10 completely different images back. And then in the case of this digital rights management situation, the person wouldn't be able to tell that this image is plagiarized, and it would be marked as no plagiarism. So before we move on, we have to go over some terminology when it comes to adversarial attacks, specifically based on the accessibility to model parameters. So there's two main kinds of adversarial attacks. The first one is a white box adversarial attack. In this situation, the attacker has full access to the target model parameters and the architecture of the model. So, and he also might have some possible knowledge of the trained data set of the target model. So this situation is very unrealistic in real life because it's not very practical for an attacker to have all the weights of a target model. But having all the weights also makes it really advantageous because it's really easy to backpropagate the loss function and generate an adversarial example in the most efficient way possible to maximize your loss function. So it's very impractical. It's very simple. The second situation is more realistic. It's called the black box adversarial attack. In this situation, the attacker has no access to target model parameters or its architecture. It's a much more realistic scenario, but it also requires a more complex approach to effectively perturb the image. There's three main kinds of black box adversarial attacks. The first one is called the gradient estimation adversarial attack. With this, what the attacker attempts to do is to actually estimate the gradient of the target model by making a substantial number of queries. They then will use strategies like zeroth order optimization, Bayesian optimization, and the natural evolution framework to optimize the image. And yes, while these approaches have shown great progress and great results in past years, the fact that they take such a substantial number of queries makes them impractical for real-world situations like the digital rights management situation. The second approach is surrogate models. And in this approach, what we basically do is we take a different model, not the model we're attacking, we take a surrogate proxy model, and we try to use white box methodologies to optimize the image on this surrogate proxy model. And then the effectiveness of the attack relies on transferability between fooling the surrogate model and the target model, where we basically generate our perturbation on one model and hope that this new image can fool the other model. Then we move on to universal perturbations. With surrogate models, again, the main challenge is this challenge of transferability. The third example is universal perturbations. And in this one, what the attacker attempts to do is to learn an image agnostic perturbation. it's essentially a noise pattern that you can apply to any image, to any input image. But again, the restriction with this is it also requires a substantial amount of queries, which might be impractical due to rate limits and the potential for detection. So now we can formulate the problem of adversarial attack for image retrieval. So we first set that 3 requirements for a successful attack. The first requirement is that the CBIR system needs to produce as many irrelevant images as possible. So the reason for this is obviously in the case of digital rights management, we want to have as many different images and as many irrelevant images so that that there's less potential for detection of plagiarism. The next thing is we want to maintain imperceptibility from the original image. We don't want to completely destroy the new image to the point where it doesn't resemble the original image. And the last requirement is a requirement we add for this project is that it must take no queries to the input model. As in the case of digital rights management, you simply submit the image to the CBIR system and you cannot continuously query the target model. This is much different than past research in image retrieval. So more precisely, for the attack goal, we can formulate it as minimizing the intersection of retrieved image sets between a clean input query and an adversarial input query. So in addition to this formulation, we can actually, acting under the assumption that the system we're attacking uses a content-based, CNN-based CBIR system, we actually can further simplify this attack goal. Basically, knowing that it converts an input image to a feature vector, we can actually see that this problem of generating an adversarial attack for CBIR is as good as trying to move the adversarial image in the feature space away from its original embedding, so that it can pick up a new set of images based on the same distance metric. More precisely, the attack goal can be redefined as maximizing the distance in embedding space between the original image and the adversarial image while maintaining imperceptibility between the adversarial image and the original image. So now let's move on to the methodology. So rather than trying to maximize the distance in embedding space between XAD and our input image, we actually attempt to guide the adversarial image towards the internal representation of another separate target image. So in this case, we take a black image and we essentially try to minimize the mean squared error between the feature embedding of a black image and the feature embedding of whatever our input image is, as we find that this direction-oriented objective leads to a less perceptible perturbation. And then as we get into an overview of our optimization process, we essentially rely on using surrogate models in an ensemble manner. And we use white box methodologies to update our input image. So we specifically backpropagate our gradient, the gradient of our objective function with respect to the image, and then we take the gradient step in the correct direction that maximizes the loss function. So just a little bit of a dive into our algorithm. What we basically do is we take K surrogate feature extraction models. And then at each step, at each iteration, we take N+1 models, and then we have 2 steps of our optimization. The first step is called Ensemble Optimization, where we optimize a joint loss function across N models. We basically hold out one model. And the Ensemble Refinement stage is basically we optimize the same loss function on the one held out model. So for the ensemble optimization, what we actually attempt to do is we attempt to minimize a fused mean squared error loss between the feature representation of our target image and our input image across N feature extractors. We're basically attempting to move the feature vector of our input image as close as possible to the feature vector of our target image across all of our surrogate models in this ensemble optimization stage. Next, we have ensemble refinement. We're basically optimizing the mean squared error loss function between the feature representation of our target image and the input image across the held out feature extractor. So we're doing the same thing, trying to move the input image towards the target image in the embedding space across the one held out feature extractor. This is a little bit of a diagram that helps illustrate our workflow. So the first step is take the input image. We attempt to optimize a joint objective loss function across 5 models. We then generate our adversarial image, and then we optimize on the 6th model we've held out, generate our adversarial image, and we continue to iterate, continue to do this for multiple iterations. So the reason why this approach actually works is that adversarial attacks, like many deep learning models, can suffer from overfitting. So basically an attack that is successful on one architecture, it doesn't transfer well to other architectures. So by basically rotating our models to optimize our objective function, we can, and by holding out models, this is similar to a concept of dropout, we can reduce overfitting and generalize perturbations to unseen architectures. And then rather than taking like gradient steps like what Ian Goodfellow did, like in the using FGSM, moving in the signum of the gradient of the image, we actually use Atom on the input image, as it's shown impressive results in improving the transferability of adversarial attacks across neural network architectures. And just a little bit for how Atom works is that it adapts the learning rate for optimization parameters by storing a decaying mean gradient of first moment and a variance second moment for each input variable. So this is a little bit of our algorithm. We basically start off by initializing our adversarial image with our input image. Then for T iterations, we first select n+1 feature extractors. We assign n to the ensemble optimization step. We hold out one model for the ensemble refinement step. Then we take n ensemble optimization steps. And in each step, we basically calculate our joint objective loss function across the n models. We backpropagate that loss to the image. And then we take a step with Atom. Once we break out of this for loop, we will then calculate the loss with the ensemble refinement loss, which is according to that held out model. We'll then backpropagate that to the image, and we'll take another step with Atom. And we continue to do this for T iterations. So now we'd like to talk a little bit about the experimental setup. So we evaluate on two main data sets, the Oxford 5K and the Paris 6K, two of the data sets that have been used in most image retrieval adversarial attack papers. So the Oxford 5K consists of 5,062 images, and it contains 5 query images for 11 different landmarks across Oxford, Great Britain. The Paris 6K dataset consists of 6,412 images, with 5 query images across 11 different landmarks of Paris, France. The models we try to attack. So in this case, we attack 3 base architectures, AlexNet, VGG16, and ResNet 101. And in addition to each of these models, we add a fine-tuned feature layer, 2 fine-tuned feature layers, generalized mean pooling and max pooling. Thus, we attack a total of 6 black box models: VGEM, VMAC, AGEM, AMAC, RGEM, and RMAC. For our surrogate feature extractors, we use 8: GoogleNet, Swin Transformer, SqueezeNet, DenseNet 121, MobileNet v3, MNASNet, ConvNext, and RegNet. So for our hyperparameters, we run a total of 20 iterations for our whole we run a total of 20 iterations for both ensemble of like the whole process. Within each iteration, we run 8 ensemble optimization iterations per step. We select a total of 5 models for ensemble optimization in each step. Our Atom learning rate is 0.0065, and the target image we use is a fully black image. For the metrics we use for evaluation, we first use the common information retrieval metric, mean average precision, which highlights the ability of an image retrieval model to return relevant images. We then use a metric we create called top 10 and top 5 knockout percentage, which is basically the ability of an attack to subvert the top K images of a clean query. And the third thing we adapt is a relevance-based loss function from another paper called Quare. And what this loss function ends up doing is it gives you a score from 0 to 15.612, where a score of 0 indicates that the 2 image sets, the returned image sets from an adversarial image and a clean image, are completely different, while a score of 15.612 indicates that the 2 image sets are exactly the same images in the exact same order. So it gives us some context into the ranking order of the images in addition to the actual images that have been returned. For the baselines, we evaluate against universal adversarial perturbations against image retrieval, which is a state-of-the-art paper for adversarial attacks against image retrieval. Despite the fact that they utilize over 1,000 queries to generate their perturbations compared to our 0 queries, they serve as a good baseline for our results. We additionally compare the mean average precision scores of we compare the mean average precision scores to those of the original target models without adding any perturbations to the input images. So this table shows the mean average precision of our 6 target black box models without any perturbations added. As you can see, they're all like relatively high. Here's our results. So this data table shows our results. We're able to beat our benchmark in most of the metrics across both data sets. And then as you can see, just for some context, like For VGEM, the mean average precision of the original model without perturbations was as good as like 80 point something. But we were able to drop the mean average precision to 6.35 by adding our perturbation, which shows how our perturbations are effectively able to affect the relevance of the image retrieval model. So some key insights. The first thing is that for the Oxford 5K dataset, our ZQBA leads to an 85% decrease in mean average precision compared to the mean average precision of the original models. In addition, ZQBA leads to a 65% decrease in mean average precision compared to the mean average precision when adding the UAP perturbation. ZQBA is also able to subvert the top 5 images of query 75% of the time on average, compared to the top 5 subversion rate of 52% from UAP. ZQBA also subverts the top 10 images 65% of the time on average across both datasets and models, and compared to a top 10 subversion rate of 48.20% from UAP. And finally, ZQBA obtains an average relevance-based loss score of 2.0 out of 15.612 across all models and datasets, compared to UAP's average score of 5.56 out of 15.612. Here's a couple sample attacks. So as you can see on the left, we have our clean input image without adding any noise, and all the retrieved images basically resemble the same image. And then by adding our noise to the input image, we can see that we affect the relevancy, getting completely irrelevant images back. So now we move on to the conclusion. So these are our key contributions for this research. We first proposed the first zero query adversarial attack for image retrieval using an ensemble approach to aid in the transferability of our perturbations on black box image retrieval models. We boost our attack with adaptive moment estimation ADAM to improve the gradient steps at each iteration. We highlight the performance of our method across multiple image retrieval models and across multiple image retrieval datasets. For further research, we'd like to focus on 3 main categories. The first is sparse adversarial attacks. Currently, we apply our perturbation to the whole input image. So we feel like by improving pixel selection to only perturb certain pixels, we could improve the perceptibility of our attack by selectively choosing pixels to perturb. The next thing is by improving model selection. So currently we are randomly selecting a set of like n models in each ensemble optimization step. We feel like by adding like a greedy algorithm or ways to better select models, we think that could help increase the performance. And the third thing is by improving the target image selection. Currently for all our experiments, we use a black image as a target image as to eliminate any chance it resembles a similar image in the data set. But we feel by further optimizing the target image, in addition to the adversarial image, we can improve our performance. So yeah, for the acknowledgements, we'd like to thank the prior research conducted in adversarial attacks for both image retrieval and image classification. Special thanks to Ji Lee and the other UAP authors for generously providing their universal perturbations, which served as a benchmark for this research. Thank you, and yeah, I'd be happy to answer any questions.